I'm starting a 30 days challenge to finish this machine learning book. That's hands-on machine learning with the Scikit-Learn, Keras and TensorFlow. So in this 30 days challenge, I will try to finish this book and learn and acquire as much information as I can extract from this book. In the meantime, uh, sometimes there needs some practical codes to do or some other things to do, but I don't know what's going on. I didn't even read this book before that, so and I don't have prior experience on machine learning. I'm just a beginner, just starting it and trying to learn as much as I can. So in this 30 days challenge, each day I'll post what I have learned, and maybe I'll go through with what I have already learned the day before. So in the day zero, I have already finished my first day part, and now I'm gonna uh, share you what I have learned there, and I may introduce you with the terms that I have been faced there. And in this challenge too, if you go with me, then you might then if you have a book with you, I mean the same book with you, you may relate to these things. I mean the topic I'm explaining. So I'll try to go and explain each and every terms that looks easier for me and I understood there. And if I am wrong, it's your job to let me correct me and give me the suggestions on that, because I'm a completely noob and starting with the zero. And remember, I'm not your teacher or something like that. I'm just learning and sharing what I have learned there, and my concept could be wrong, or I mean if I understand a concept in a wrong way or that's not valid, then please feel free to correct me and comment below, so that I can correct myself also. So yeah, basically these books is I think it cover pretty much things. For example, understanding the data, understanding the basic concept, to like how machine learning projects work, how training work, how, like, I mean a lot of things, man. So huge thanks to Miss Misbah Ahmed, because like he gifted me this book so that I can expand my knowledge on that. So yeah, thank you to Intelligence Academy and Ms. Mohammed Bhair. Thank you so much. So before I started, let's go back to the main fundamental things that I have learned here. So the deep learning is basically introduced by Zio Offrey Hinton, if I'm not pronouncing wrong. So in 2026, so there, I mean, he published a paper where he trained a model by writing himself. I mean, he trained a neural network that is able to recognize handwritten digits by computer or machines. So then they branded this technique as the deep learning, and this is how the deep learning came seen. And I mean, before that part, deep learning was kind of impossible things. People can't go through it, and he solved it. And that increased the things. I mean, for example, the YouTube algorithm that you see, the Facebook algorithm that you, I mean, the way they recommend you, the Amazons, the way they recommend you the books or something like that. So everything's comes in, and everything has been integrated with machine learning and deep learning. For example, I mean, I'm not saying everything, I'm just saying the example that I have shared. So for example, the self-driven car, we all know it's AI, right? But what if the OCR, I mean the way we recognize a document, I mean from image to text generation. For example, so if you go to the GPT model, they also have OCR, right? So if you just take a picture of your document and send back to the GPT, then it's generate the text and it answer that questions to you. So everything from then has been revolutionized a lot of things, and these books covered part of it. So the main objective is like in this book we're gonna be learn maybe Scikit-Learn, TensorFlow, and Keras. So what does they do actually? So I mean the objective and approach of them. Scikit-Learn is very easy to use and implement in many machine learning algorithms. If for efficiency, it's a very great entry point for anyone to learn machine learning. And then it comes to TensorFlow, which is, a complex library of distributed numerical computations that has been developed by Google. And then it comes with Keras in a high-level deep learning API. So Keras is a high-level deep learning API that lets you communicate through deep learning or machine learning neural networks through API. That's what I have learned actually. Assumed by reading this. So in this book, they have shared some free resources and the tutorials as well, from internet. So now let's go back to the what is machine learning. So basically, what do you know? Machine learning is a model or something that where we have some data to train a machine or robot to take some decisions around that. So let's learn that in a good way. So in this book terms, it says like machine learning is the science and art of programming computers so that they can learn from your data. So yeah, this is what machine learning is, and there's a lot more definitions behind that, but I think that's the easy one. So then why to use machine learning? I'll try to summarize everything in a compressed way. Maybe that's not understandable to you, but the video is gonna be very long because if I have to complete this book in 30 days, and if I gonna deliver you all of these things, this is almost 900 pages book. So that's gonna take a lot of time if I don't compress the video in a short. So yeah, if you want to dig deeper into the terms I'm explaining, please feel free to go and take this book and have a look into it. And this book have a very, it's a very rich information covered with. So I'm not used to read books regularly, but after reading this book, this is my second book that I'm reading that much actually. So I only read that one day, but I have already finished almost about 37 pages, alhamdulillah. So this is the book that I'm feeling interested to look into it. So if you also feels like the terms I'm sharing with you, that's something connect with you, feel free to go with online version first if you think, and if you think you can take a book physically, buy a book physically, then go for it. So yeah, why to use machine learning? So machine learning models comes after, to train a model, to train a program or robot, you need to let them choose a way. For example, there are two paths which way the robot will go, left or right. Before machine learning, we have to explicitly program everything, like you have to go there, you have to go there, you have to go there. But after machine learning comes in, the robot can automatically learn themselves. That's called reinforcement learning. And there are some also other learning methods like supervised, unsupervised. We'll come to the later. We'll come to that later. So why use machine learning? This is basically to avoid explicitly programming so that the computer has some brain and they can take their decisions. It's common to our cerebral cortex, but it's not that high end right now. But it's getting to update day by day. Then there are many ways to learn machine learning models. So basically, I'm just taking you through the terms that I have been noted in my book. So yeah, digging into large amount of data to discover hidden pattern is called data mining, and machine learning excels at it. So if you have a lot of data, for example, if you have a business, for example, Arrow have the sales data, and now they wanna train a model, something like Amazon's have. So Amazon's, what do? They suggest the people like you who bought this product. The same product you bought, the people also bought on this bucket, something like that. I don't know what the exact term of that, but it suggests you some product for the product that you have already chosen, right? So in the same way YouTube have the algorithm. This is gonna be easy way actually. So if you watch some videos on Facebook or YouTube, and you will then receive some suggestions or recommendations from Facebook or YouTube algorithm in the same way. For example, if you watch a video of a sheep, then probably the next few video you are gonna be recommended by sheep. I mean the same category that you have been looking for. So this is all happening because of machine learning. In this book there are some examples of applications that's been mentioned here. So for example, analyzing image of product on a production line to automatically classify them. For example, if you have three color of product, I mean you need to classify. For example, let's see about a chips factory that's produce chips from potato, right? So you have to classify and identify the dummy potatoes maybe, so, or the what does it say? So sorry for that. So you have to classify the good potato that are healthier and well for your process to make it, and you have to eliminate all the bad potatoes or all the chunks that comes through the potato bags. So you have to explicit them, right? You have to exclude them from your good healthier potato. So this is how you are using cameras and machine learning models behind the processor, and then you are classifying them and deleting the extra part. So there are a lot of examples and applications to give you an idea about how we are using these things. I mean, a lot of things that's been covered up here. For example, forecasting for your company sales and revenue. Yeah. Then types of machine learning systems. So in the types of machine learning system, it comes with a few different learning models. I saw Mesovaya videos where he showed like 118 machine learning models. So there are a lot of learning models, but not all of these covered in this book. It doesn't have to, right? Because it's covering already a lot of information about a whole overview of machine learning. So if you want to dig deeper, then you may do your own research. I'm just sharing the models that have been here, and I'm sharing my thought on that. So training supervision. Okay, so supervised learning is something like we're giving a machine learning model in a level way data. For example, this is my hand and I'm detecting this as my hand to the machine learning model, so that it can be trained to detect this is a hand of a person. And this way we are detecting and leveling each and every data. For example, let me give you examples in real life. We all use Gmail, right, or email inboxes. So how do your email inbox detect the spam? There are a lot of emails comes in, and they are detecting your, why we are leveling this is as a spam, this as a promotional, this as a marketing, or something like anything that we are leveling them, and then we're training our data. Once the model is trained on that data, then it can detect any unleveled data or any new data that's coming into your system, and that's how it's automatically detecting your emails that comes through, and it detect most of the spam messages to push it to your spam folder. How do they learn them? How do we train them? That's gonna comes up later in this book maybe. But yeah, this is what supervised learning is. Then it comes to the next, unsupervised learning. So there are a few tips that have been shared in this book that says like the word target and level are generally treated as synonyms in supervised learning. That means target and level are generally the same, but target is more commonly used in regression tasks, and level is more commonly used in classification tasks. So in another word, what is regression, right? So regression is part of linear regressions maybe. So there are a fun fact about regressions that is like a scientist, maybe the Francis Galton, who used to, who had a children who is tall that the children of tall people tend to be shorter than their parents. Since the children were shorter, he called this regression to the mean. This name was then applied to the method he used to analyze correlations between regression variables. So what is regression actually? So typical task is to predict a target amount value such as price of a car or these things. Uh, a typical supervised learning task is classification. So then another typical task is to predict a target numeric value such as predict the price of a car by given to the mileage, age and the brand name, etc. This sort of task is called regression. To train the systems, you need to give it many examples of car, including both their features and the targets. So, for example, you wanna do house predicting, house price predicting model, right? So then you are using a regression model. What it is actually, you are giving some variables like this house is how much square feet, how many bedrooms, how many bathroom, or blah blah blah, and then you are giving it a price in a level way. For these things we are getting this price, and this way you have multiple data about that, and then you are giving it to a regression model, and then they are predicting the price of the, I think that's it. So let me know if I'm wrong. Then it comes to unsupervised learning. Unsupervised learning is basically you are giving a bunch of data without leveling it, and then the machine learning model is clustering your data by watching them. For example, it's a good example for meta Facebook ads. So how do they perform? How do they know this person is going to be buy from you or not? Your job is not to buy anything always from Facebook, and then they can't level you, right? So in this way the unsupervised learning is, they're clustering the peoples by looking for the activities and engagement all over the Facebook activities, and then they're predicting like this type of people or this cluster of peoples are maybe interested in this bird, and maybe some of that cluster people might be buy from you, and then when you're promoting something to them, then they're showcasing this product to that cluster, and then some of them probably buy from you. So this is how unsupervised learning maybe work. Yeah, that's from my understanding. Then there are a few more terminology that's been introduced here. For example, feature extraction and some of the other things which I understood, but on the time when I'm reviewing this, like if I gonna review all this term, that's gonna take a longer video. It's already 18 minutes here. Okay, so then it comes to semi-supervised learning. Semi-supervised learning is basically the mix of supervised and unsupervised learning. So most semi-supervised learning are the combination of unsupervised and supervised algorithm. That's it. So that means like you are giving some trained data, and now your model is using that data to train itself, and then classifying the rest of the data, and it's learning itself, something like that. So for example, here we have an example of like self-supervised learning example, that recovering a caddy maze after after part of the caddy maze has been deleted. So this is how supervised learning, this is what self-supervised learning is. Comes to reinforcement learning. So reinforcement learning implements the robot to learn itself. For example, many robots implement reinforcement learning algorithm to learn how to work. DeepMind, AlphaGo program is also a good example of that. This is the robot that beat KG on the game in 2027, May of 2027, and that been on the headline on that time. So this is how reinforcement learning. They learn themselves by rewarding systems. Then it comes to batch versus online learning. So on the reinforcement learning, we get introduced to offline learning. Offline learning is basically you train a robot first, and then you are turning off all the way to it learn itself. Then it have a memory how they learn, something like that, and then it using that to work for the next time. I mean for the next project or something like that. Then it comes to batch learning. Batch learning have some disadvantages also. So basically batch learning is you are in batch learning, the system is incapable of learning incrementally. It must be trained using all available data. That means like you have a lot of that, I mean you have to train your robot once, and then if you have any update, then you have to train the whole data scenario again. And this is the problem. Sometimes that becomes impossible for the big for a big project or a big model to train them with the whole data. So this is not a very practical for someone, but for, I mean, yes, that's it. So if you want a batch learning systems to know how about new data, you have to train the systems from the beginning, I mean from with the whole data. Let me clarify you in a bit more clear. You have three tier data, okay? Then you are training the robot with three tier data. Now you have one update, that's called level 4. So on the level 4 you have to also train the whole model with this existing 3 data and 4 again. It's not something like you're just upgrading, I mean merging the new update. It's about the training the whole system again. This is what the batch learning is. Then it comes to online learning. Online learning is basically your system is incrementally feeding the new data. That means you have a new data, I mean you have a trained data. For example, let's say about airport flight tracker or something like that, or stock live prediction, I mean yes. So if you want to predict or see or examine the stock data, they are changing rapidly, right? So then you have to then your model have to learn incrementally. The moment they'll learn, that's not going to be the way it learn. I mean, if your system has been learned something previously and then you're using that, that's not going to be work there. So this is why it comes for online learning. They either individually or a small group of called mini batch. So in this online learning group, they might be learned individually, or a small group that called mini batches could be used there. Then it comes to the next, I mean okay, there is another method or a term that says learning rate. So if you set a high learning rate, then your system will rapidly adapt new data, but it will also tend to quickly forget the old data in online learning method. But if you if you like rate the learning data in a lower, I mean lower learning rate, your data will have more inertia and it will learn more slowly, but it will also be less sensitive to noise in the new data or to the sequence of non-representative data points. So the point is to balance the both so that your model can be better here. Then it comes to instant based versus model versus, I mean instant based learning versus model based learning. Another more categorized way of machine learning systems to learn how to generalize things. So in machine learning, we're basically generalizing the things, right? So having a good performance measure on training data is good, but insufficient. The true goal is to perform well on new instance. So there are basically two main approaches of generalizations of how a machine learning generalize. The first one is instance based learning, and second one is model based learning. At first we're going to be explore with instant based learning. So instant based learning is basically you are giving some example of data, and then your model is now like measuring the similarity, okay, between them. So by using a similarity matrix to compare them to the learning example. So basically you have trained train some data with some learning data, and then you are testing with the new data that's been not been trained on that model, and then the model is now comparing the similarity, and depending on the similarity that matches, it's classifying the data. This is called instance-based learning. So there is some figure here that makes the learning on understanding this concept easier, which might not possible in this video. I mean, for me to showcase them and edit the whole video. So if you feel free, or if you have some confusions on that, just go through in. And then model-based learning and typical machine learning workflow. So typical machine learning workflow is another way to generalize from a set of example. Is to build a model of this example and then use the model to make prediction. So basically you are generalizing some examples for the machine learning model, and then you are giving it to the model, and then they are making the predictions into your model. You are not training all of them, you're just giving some trained data, and then the machine learning model is going through whole data and make prediction into on the whole data, so that they can classify the data themselves. So then there are some math example for linear regression. For example, it tracking the happiness satisfactions with some examples, so that we can understand how linear regression is work, linear model work. So basically there are two type of linear model as I have learned so far here. That is linear regressions, and another is polynomial regression. So okay, so how can you know which value will make your model perform best? To answer that question, you need to specify a performance measure. You can either define a utility functions or fitness that measure how good your model is. So a fitness function measures how good your model is, and another model there is a cost function model that's calculate how bad your model is. So then it comes to the next okay, the main challenges of machine learning data. So there are two type of main challenges. One, the model could be bad. Second, the data could be bad. So at first we are going to go with data, how a data could be bad and insufficient. Okay, so in general life, how a toddler learn, right? So you are showcasing them like this is an apple, so they're recognizing it. You might need to repeat that 2 or 3 times, but then they'll learn it. But what about machines? They don't have intelligence like ourselves. They learn from a lot of used data to recognize just an apple. It's not like your baby or toddler. So they have to learn about color, they have to learn about shape, they have to learn about the size, a lot of other things that's been depending on there. So all of these data you have to put into the model, then it will be able to recognize that apple. Otherwise not, it might do the wrong predictions there. So this is how crucial to have a lot of training data to train a simple model to just recognize apple. And in term of having some data to train this model, it takes a lot of time for the data scientist or the person who is training our model. So that's why the insufficient quantity of training data might lose your model prediction quality. So it says like very different machine learning algorithms include fairly simple ones perform almost identically well on a complex problem of natural language once they were given enough data. So there are some reports that has been recently published that like ChatGPT, Gemini, and all of these others, GPT versus chatbots that been released over internet by different organizations like OpenAI, Microsoft, or anyone. So they are almost becoming same in order to answer the same questions. So a person who have been gone through all of these models side by side and with the same questions, and the output become much more similar to that. So this is what means, like there is a paper in 2001. A person a Microsoft researcher Michael Benko and Eric Brill showed that report that when you train a machine learning algorithm, it's with a fairly similar data, but it will identically perform the same if the training is almost uh, if they are trained with well data, something like that. So I have some confusions on that. Not in terms of that the book says, but I have to do some bit more researches on that. So yeah, I'll get back to you if you think that's what you wanna discuss about. Then non-representative training data. So non-representative training data is make it clear to such a simple linear model is probably never going to work well. So that says like, okay, you have trained a model with a bunch of data, but is it gonna be work for all the times? Is it gonna be work for all the use cases as well? But no, it says like you can't say your model is good when you're just trained a linear model in a proper well way. So to perform it in a, I mean, this is hard to say, man. So basically, the thing is like it makes it clear that such a simple linear model is probably never going to work well. So maybe you have understood what I have to say. It's crucial to use a training set that is representative of a case you want to generalize to, and this is often harder than it sounds. If the sample is too small, if the sample is too small, you will have sampling noise, but even very large sample can be non-representative if the sample method is flawed. This is called sampling bias. So biasness is basically you have a data. Okay, let me give you an idea about what is biasness is. For example, you are going to ChatGPT and asking for like give me a picture of a cat, but in general, if you just say to someone, we can recognize the most familiar cat that you have been shown, right? But how do AI recognize them? How do AI recognize which breed, which color, which type of eyes, which type of what does it say? I just forgot. It's about loam in Bangla. So anyway, so just it's not getting into my mouth. So the thing is like, how do they detect them? They are adding bias here so that can be used to get sent back to their model, so it's working, and then it generate a image of that cat to you. So this is how the biasness is getting added to the system to make the output a good to you. So there are different type of examples of sampling bias. Then it comes to poor data quality. So in general life, or really, data never became, data can't be clear every time. The data is full of noise and some of others data. Sorry. Okay, so the next term is poor quality data. So obviously your data is full of noise, error and outlier. So most of the time, if you train your model with these with the data that contain full of error, outlier and noise, then it's obvious that your model that's not gonna be work or output as well. So most of the data scientists spend a significant of their time to clean their data, to remove some noise or outlier from that. So yeah, then irrelevant feature. So a critical part of the success of a machine learning project is coming up with a good set of features to train one. This process is called feature engineering. So for example, we are predicting a house, okay, house price, and then the feature is called the table, okay, the column. So you have a different type of table or column. For example, a house price can be detected with something extra data. For example, how does it say? I never bought any house, so I don't have any idea about how house price get detected. So anyway, I'm just giving you an example. A house price could be measured by depending on the location, maybe the roadside or not, maybe how far from the town, or how good quality, how many floors, how many rooms, or etc. other things. But think about what is not related to the house. For example, your house. Uh, what do they say? Your house have a tree or not? Is that gonna be predict a house price in general? No. So this is how the feature engineering work. I mean, you are excluding all the extra features that are irrelevant to your product to predict the prices, and you are excluding them. This is called irrelevant features, and this process is been called feature engineering. So the feature selections, the feature extraction, and creating a new features by gathering new data. This is the following step of the irrelevant feature extraction. Then it comes to overfitting the training data. Okay, so there are two type of things. There's been there overfitting and underfitting. Overfitting is basically you are overgeneralizing the things. Let's give it as short example. For examples, you are going to New York or China, then you are taking a taxi, then the taxi driver snatched your handbag, or like something like that. That don't happen really. I mean, that doesn't mean the all taxi driver in New York are snatcher of your bag, right? They're not bad, but you are assuming that okay, maybe New York people's taxi drivers are so bad, something like that. So we're basically over generalizing the things, and the same trap could happen with your machine learning model. This is the same things that's called overfitting. So that means that your model perform well on trained data, but it does not generalize well. So it understanding everything, but it's not able to generalize in real data or the test data. For example, complex models such as deep neural network can detect subtle patterns in the data. But if the training set is noisy, or if it is too small, which introduce sampling noise, then the model is likely to detect pattern in the noise itself, as in the taxi driver example. So overfitting happens when the model is too complex relative to the amount and noisiness of the training data. So here is the possible solutions how we can eliminate overfitting. So simplify your model by selecting one with fewer parameters, then gather more training data and reduce the noise in the training data. So the noise and outliers are a very big challenges for any machine learning models to perform well. So we have to handle them in a careful way. So constraining a model to make it simpler and reduce the risk of overfitting is called regularization. Then it comes to hyperparameter. Hyperparameter is a parameter of a learning algorithm. Okay. Then what is underfitting? Underfitting is exactly opposite of overfitting. So as you might guess, underfitting is the opposite of overfitting. It occurs when your model is too simple to learn the underlying structure of the data. You have a simple general model that you are giving to understand your data. For example, I'm giving ChatGPT to ChatGPT is a pretty solid model. Let's think about something less. For example, you are giving children to drive a car. I mean, you are giving a 3-year-old children to drive a car. They can't do that, right? So the children have to be more conscious and have to have more sense and power to handle the steering at least, right? So this is how it comes. Underfitting. To eliminate underfitting, you have to select a powerful model with a more parameter, then feed better features to learn algorithm. The children have to be more conscious, as I said. Their brain need to be developed so that they can learn more algorithms and features. Then reduce the constraint on the model. For example, by reducing regularizations hyperparameter. I mean, you are just reducing the extra constraint that's been there. Then this is all what cover in chapter, but there are something more that called testing and validation. So basically testing and validation is you are calculating the generalization error. In general case, we often go to the ratio of 80-20. 80% is for training the model and 20% is for testing the model. But for example, if you have 10 millions of training data set, and in that situation, do you think you need to have like 2 million of data set to test the model? No, you might have 1% of the data set, that is enough, far more enough to test your model how they are performing, right? So how do we calculate how do your model is working good or not? This is what how we, we used to train the model with some level data, and then once the training is complete, we are using some trace or unlabeled data that we never train our model with that, and then we're checking them if they're working good or not. So yeah, this is how we practically train a model. Then it comes to, like, there are some other terms that calls holdout validation. Holdout validation is basically you are holding some of your testing data, and in simpler way how I learn, I think I could be wrong, I have some confusion on there also. So the best part is the holdout validation method. It is basically, okay, so if I say it more specifically, you train multiple model with various hyperparameter on the reduced training set, and the reduced training set is the full training set minus the validation set, and you select the model that performs best on the validation set. After this holdout validation process, you train the best model on the full training set, including the validation set, and this gives you the final model. Lastly, you evaluate the final model on the test set so that you can get an estimate of the generalization error. So basically, we are splitting our testing data set. This method is gonna only work if you have a huge data set to train on your model. Otherwise, that's not gonna work that. So you are just splitting your data set, and you can't test all of your model, right? You can't test all of the model, that's not feasible anyway. So what you have to do, you have to just splitting the data set and training and assuming like which model gonna be maybe work, then giving it some sample of data so that they can evaluate the model which one is performing how, and then you are just checking which model performance is good, and then you are selecting the model so that your rest of the data set gonna be trained on that model, and then you are re-evaluating the system, and this way you are getting a pure model that's been working for your data set. It's not mandatory that all the good model gonna be work for you, because the data depends on things. So if you have a clear data, or a model that work for point A, they're not gonna be work for point B. So this is how the generalizations work actually. So you have to test your model that's gonna be work for you. That's it. Then it comes to data mismatch. The most important rule to remember is that both the validation set and the test set must be a representative as possible of the data you expect to use in your production. So in a common sense, if we say that, it is basically you are using a data to train your model, and then you are when in real life production you are using the model with a different type of data that doesn't make similarities to the training data you had. In that time, the performance of the model that's not gonna be good. So you have to make sure that you are using the same data that you have been trained, not exactly the same type of data, and then you have to just make and then you are using the same type of data in production. This is how we are connecting the training and the test data, connecting together to make the model working good. So this is called data mismatch. Like for example, it shared a model, like you are taking you are trying to build a flower detection or classification model. Now you are collecting the data from internet, and for the real life or the real scenario, you are detecting that model with your mobile camera. So the difference is the internet picture are not same as your mobile picture, because they might be using proper, better camera, might be using better image retouch models there to retouch their image in a proper way, but your mobile phone camera is not doing the same things, right? So this is how the data mismatch comes and the model performance drop on the certain productions. So then it comes to the end of this chapter. So there is another terminology had been introduced here. In a famous 1996 paper, David Olpeter demonstrated that if you make absolute no assumption about the data, then there is no reason to prefer one model over any other. This is called no free lunch, NFL. So there is no model that is priori granted to work better. The only way to know for sure which model is best to evaluate them all. So you have to just use the model and check if this model work for you for the best or not. And this is why most people try to work on different model and see which performs better and pick one, or they might use ensemble methods to in their real life production. So there are far more things that's been after the chapter 1. I've only finished the chapter 1. This is just gives an idea about how machine learning works and what is machine learning. And I think the more we are gonna be drive deeper, we're gonna be get more information about it. So that's it. If you are watching this video to the end, maybe you're the lucky one. So not the lucky one, I'm just saying. So basically this is what I'm covering. In this 30 days challenge, I will go through this book and then cover as much information as I can. This is for personal challenge, and let's make it happen, and let's see how if I can make this challenge complete by day 30 or not. So this is day 0 of day 30. See you in the next episode. Thank you. Bye bye.